Okay, that will be the second part of the course on linear maps. And as I told you, I'm not that concerned about the quality of the video and, well, about rigorous planning. So it might be that I'll do some other things while making the video, for example, eating or things. So I'll be pretty relaxed. That's just meant to happen like that. So, and well, from time to time, I will then write something on the board and will derive some things, get some definitions. So, as it was. But yeah, I'm not that concerned about the general quality. So, you'll see. Okay, where were we? Oh, that's interesting. But I don't think that we need it. So I'll erase that quickly. So let's see. Well, linear maps. It's supposed to be an S. Sorry, linear maps course. Part 2. Okay, let's define a linear map. What is it? Definition. By the way, we'll need, of course, some basics from vector spaces to actually make some proofs work. I don't know yet how I will give them. Maybe I'll just make some intermezzo's. I mean, some auxiliary stuff within the proofs. Maybe I'll do separate videos for that. Don't know yet. Well, just now I'd like to look at linear maps, and that's how I will do it. So, definition. A map. L, big L, from V to W, V, W vector spaces, and that means here vector spaces in the sense of our general definition of vector spaces from before, right? We don't assume anything else now. It's called linear F. Well, the following two conditions have to hold for all E1, E2, and V. We have to have that the application of f to the sum of v1 plus, that's supposed to be a 2, but let's correct it, write it properly. Alright, the sum of, what is it? I don't get it. What's wrong? The sum of v1 and v2 is equal exactly the sum of the evaluations of f v1 and f at v2. So it's like we can kind of interchange where we first apply the sum on the vector space V, and pay attention here, it is the sum on the vector space V, and then apply F to bring it to W. So this thing is in W, you know, this is in W, just by definition of a map, it goes to W. And this sum is of course the sum of w in W, not the sum in V anymore, even though we denote it by the same sign plus, because it would be a hassle to always introduce new symbols for operations with the same meaning on different vector spaces, but with the same respective meaning. So we don't do that. But this is of course sum in W, and so this is in W because plus in W is also closed, right? So pay attention here, plus is in V, here plus is in W. Okay, so we have this kind of compatibility of F with the operation plus. Right, and well, what would you guess for all lambda k? Oh, of course, I mean, as I said, all vector spaces for now are k vector spaces, unless otherwise mentioned. All vector spaces are k vector spaces. I mean, with the same field k. All vector spaces are k vector spaces. Oh, that's self-explanatory, but with same k, with same field. Okay. By the way, I would recommend that you really write the things down, especially because of my not necessarily nice handwriting. So for all lambda in k, for all v in v, we have that lambda v, this scalar multiplication. If we apply f to that again, scalar multiplication, this length in v, and this is of course scalar multiplication in W. Right. Right. This is also compatible with the scalar multiplication. Right? This is such a map that is compatible with addition and compatible with scalar multiplication. This is all what we have to know about linearity. So maybe some examples are in order. Let's say we just consider, well, what do we consider? Okay, wait a minute. I have to check something. Alrighty. So, where were we? Right, some examples of linear maps. And also some, well, you could call it applications, but we'll see about how to call it. Examples of linear maps. Probably you can name a linear map that you know very well right off the bat. Oh, let's see if you can check it. That map is supposed to go from R to R. R is a vector space, particular, for example, R vector space, so no problem with that. And this map is supposed to be very well-known function gx is just ax. By the way, this equal we could also write like this. That means exactly the same as here. This is the rule for the map G, how it maps an X. And could write that this is the rule of G. So yeah, there are different possibilities. And this map is of course linear. Well, you can check it really easily. Distributive law applied. This is like L of G. Sorry, it's not L now, it's G. Now has become G. Okay, G of X plus Y, right? Because this rule is given exactly by this, A multiplied by something, and we just apply distributive law, right? No magic here. And this is, of course, G of X, this is G of Y, so that's obvious. And you can probably also already see that by the associativity of multiplication R, we just get, and by commutativity also, if you like, lambda AX, which is exactly lambda J of X, lambda G of X. Right, this was the most basic example. What else? Well, generalization of that is, of course, that we have a matrix M and some R K cross N. Remember matrices from the last time? Well, probably you should be familiar with matrices, I would say. And we have some V and R and cross 1 and M is M defines a map LM from R and cross 1 to R K cross 1, which means N rows 1 column, K rows 1 column, and of course you're familiar with what that is, just Rn, and that's the sign by which I denote correspondence, right? Okay, and of course, what else could it be? Lm of our vector V, which is defined to be M multiplication of a matrix M with a vector V, right? And this, of course, just by how the matrix multiplication is defined. That's our okay. Right. Also, maybe we'll already drop this distinction in the subsequent considerations when it's clear that we consider matrix and we consider the corresponding linear map. We'll just blur this distinction and just call this linear map M, just the same, not LM. M defines this map, but we will call this map just M. There will be probably no confusion. That's the usual thing to do, so we'll do it just like it's always done. Right, what else could I give you as an example of a linear map? Well, all right, let's do something fun. You probably recall that we had this funny space C0 closed interval 0, 1, which was defined as the space of all maps from interval 0, 1 to R such that F is supposed to be continuous. Right. And what could be our linear map? Well, we just do the following. We want to integrate. You probably wonder what an integral has to do with a linear map. Well, you'll see in a second. We integrate our something that is here. We could just plug in any function. So pause for a moment in your mind and just think about it. What it means that we could plug in here any function from this set and integrate it. So that we plug in a function from this set means that we go from here And the integral gives us a real number. So if we compute this definite integral, then we get the real number, which is r. That is, here is some f from the set. And if we compute this integral of this plugged in f, then we get a real number, because integral is defined as a real number. And that this is indeed well defined. Well, you know it from school. Well defined since that's Riemann integral for now. Okay, since f is a continuous function on a closed interval. And all that continuous real-valued functions on closed intervals are definitely integrable, right? All right. Right. And what could that do? Well, of course, it's just a science for each f, the number which is exactly this integral. And that it is linear, well, it's just linearity of integral, right? Yeah, that this is a vector space. You should have checked last time yourself, but yeah, it's easy. We also defined the operations, right? So you can look it up in the last video and you can check yourself that it is a vector space. All right. This is just linearity of integral. You know it from school, right? And yeah, don't get confused or afraid that we have such funny definitions like integral is now a linear map. Just think about what is applied to what and think about how it makes sense, and you'll see that it makes sense just perfect, right? All right, and this is again linearity of integral, the other property of linearity of integral, that we can take out a constant, right? Alrighty, now do something really fun. We'll do something really fun. That is, why do we need linear maps? Why the heck? Why do we need linear maps? And now I will give you something by which I won't be as rigorous as usually. Okay, let's see. Why do we need linear maps? Consider a map f from V to W, which is not necessarily linear. First, it is just a map. Now assume that this map is differentiable. What exactly that means? Well, we know that in the case of functions from R to R. And the general differentiability is just a generalization of that particular differentiability, right? But the interesting thing is the class of differentiable maps is much larger than the class of linear maps, as you already know, in the simple setting of the maps from R to R. but this also holds generally that the wealth of the maps that can be differentiated is generally much larger. And what is actually the meaning of differentiability? Well, turns out that differentiability is the ability of the map to be approximated by a linear function. What does that mean? Well, let's say, probably I should do it differently, but no, let's do it like that, okay? So we evaluate our map f at some x plus x0, and here x is supposed to be chosen point, and x0 is supposed to be a small deviation from this point. But the catch is now x is just any element in this V. So V could be R or R2 or even some crazy abstract vector spaces that we can't even imagine, right? Right, okay, we just have this map, we can evaluate it, that, why not? And let f be differentiable at x. Then if f is now differentiable at x, that actually means in the grown-ups math that there is such a linear map that allows the representation of f being approximately equal to this kind of generalization of a line. You see, this is some linear map, right? Usually in the case, in the case that you're familiar with, L is just equal A, that's a real number. And this is approximately equal, right? A is just a real number. And then this is just your familiar line, right? Fx plus Fx plus Ax0. So you recall probably that if we have a differentiable function, let's just take parabola, right? Negative part of a parabola, something like x squared, right? And we have this line, and this line has slope a, that is, this is angle alpha, and well, okay, no, I shouldn't do it like that. Sorry. Of course, this angle is counted in this case differently, because you want to have negative tangent, right? So we have to have an angle that is larger, 90 degrees. So this is alpha, and the slope of this line is a tangent of alpha, and the line is then exactly, this is our function f, right? And okay, that's variable x, and also the point is called x, but you manage, right? I could call the point x tilde, but it doesn't matter. So this line is L equal f of... okay, I shouldn't write that because it's not actually L. L is just a plus x0, but this line, we could call it, I don't know, small l. Now x is equal, actually, of course, yeah, wait a minute. Yeah, L of x0. Linear map now applied to x0 is a f of x plus a x0. And you see, it doesn't matter how I call the variable, what I call the variable. I could call it z, I could call it x0. The only question is what are the structures in which this variable appears and what role it plays in the structure. So this kind of structure means it is a line, right? And it is this line because this is here f of x, this point here has coordinates x, f of x, but this is the point at which we have the value f of x, and we have considered the derivative at this point. This derivative has this slope, and this line is given by f of x plus a x0. Right? This is just the derivative. It's cool. All right, and now you could imagine that somehow this is generalized, right? And as you know, of course, it's not like the function is equal. I mean, we are now in the simple case, right? In this case, it's not like we could write of course it's not equal unless f is itself linear, but well, that thing we probably won't have like that, right? But if f is itself linear, well, you could guess that it's just some b multiplied by this, like just like we had this example of the most simple linear map from R to R, b multiplied by x plus x0, and well, just apply this, and b is exactly the slope. So if we take this line with slope b, then its derivative is of course b, so it will be true. But if it's not itself a linear map from R to R, and of course, this won't be true, right? But here we don't have equal. We have approximately equal, which means that so this is approximately equal to 0. So this is not 0, but it's approximately equal to 0. And that is, we could think of that remember, x is just a fixed point. So we could think of that as depending on x0 and being some function depending on x0 that is very close to 0, that is approximately 0. And of course, that only works in the proximity of the point x. So if x0 is very close to x, then this function, if it is differentiable, and it is linearizable into the very proximity of this point x, somewhere here. The function looks kind of like a line. Okay, I have drawn it badly, but if you think about that, you see something like this. And you see that the function is basically the line, but in very close proximity of this point x, right? I have just drawn this segment of a picture here. Right. So this is equal to some function that is approximately 0 in the proximity of this point x. Right. This is interesting. Well, and as you can imagine, it would be just natural as x0 goes to 0, this function should go to 0. But this, of course, wouldn't be enough, right? Because if we had that, then recall school, you would have x plus x0 minus f of x. Recall the characterization of differentiability at the point x given in terms of a limit. And of course, if you would just have that this somehow goes to 0, and this also goes to 0, and this now can be represented as this. So we get like, we get this limit, right? Then this, of course, will go to 0 as well. But if we just have that this also goes to 0, so let's suppose this goes to 0 and this goes to 0. Then this, of course, would not suffice to tell if the limit exists. For example, if you have something like that, well, that would be to infinity, but okay, let's say you have something like that, and you have something like that. That is a sequence where you actually have that this is equal to n, and that goes to infinity. The limit does not exist, right? So if that goes to 0 and that goes to 0, it does not suffice for the limit to even exist, right? All right. So it would not suffice to just say, well, this function goes to 0. Of course, we also have this term here. If we bring it here, I mean, like, we could wait a minute. We could just, if we would suppose that this exists, right? Let's suppose that the limit here exists. And as we know from school, that would be the derivative. So we would have some a, and a multiplied by x0 divided by x0 is x0. Then we'd have to consider this. And of course, if that limit exists, if we take a away from the limit, we can also plug in a in the limit, which I already did. It's just calculations with limits, right? And this limit would also exist. And if we just have that this goes to 0, we have already discussed that here, and we have that this goes to 0, and it does not say anything about this limit. So it does not say if it exists. So, and correspondingly, if we would have this limit exists, we could just take a, add a to this, which is just this, where I have eliminated x0 here and here, we would get this limit, and that means that let's call that limit lim1, call that limit lim2. Independently whether they exist or not, we don't know. It's just mathematical objects, maybe infinity, not numbers, mathematical objects. And we have that limit 1 exists if and only if limit 2 exists. That is, we have looked at this, right? And we have realized, not a rigorous way, but more or less, we have realized that for us to have that when this goes to zero, this goes to zero is not enough to conclude that the function is differentiable. So it is not, yeah, it is not enough for the function to be differentiable. There could be functions that satisfy this, but are not differentiable, which means that a differentiable function must satisfy something that is even stronger, right? Because if there is a function that is not differentiable and still satisfies that, then a differentiable function should satisfy something even stronger. Right. All right. Let's see. All right. Wait a minute. Right. And what is this stronger? Well, turns out that for function to be differentiable, we have to have such a linearization with such property. Now, linearization means just that we can approximate function. Can approximate the function like this. And of course, that we can always write down. So if this function has no properties, of course, we can always, for each x0, x is fixed, remember, we could just define this function to be that, right? That's no problem at all. The question is how this thing behaves. Whether the approximation becomes better and better, and it does not suffice that it becomes better and better, as we have seen here, whether it becomes better and better in a strong way when we approach x. What does it mean? Well, it turns out that the approximation has to satisfy the formal property. This should go to 0, and that means that this function should actually go to 0 faster than linear. Right. And that is faster than linear disappearance. Of course, that is since I have taken that, though that argument that we take here to approach x, we have that this is close to 0, not to x. Otherwise, well, wouldn't have anything to do with our considerations here, right? For x0 to 0, right? And well, as I said, this is the simple case of the derivative where the function f goes from R to R. So we took the parabola here of illustration, but of course we mean it more generally. We mean the case of function from R to R differentiable at x, right? Now, I told you that we actually have it more generally. We can have more general differentiability, but we won't go into it for now. We'll just state it and think about it a little. More general differentiability works just like that. Now f, let's call it f tilde, but pay attention, it's just important that the structural relationships in which the object are the objects are, they are the same. So it's not important what I call it. So now I'll call a thing with respectively same properties f tilde, right? And this is now a function just like above from a vector space V to a vector space W, and we suppose that it is differentiable. And we won't go and give a definition now. We just say, well, differentiable means linearizable. So, but now remember that f is just some crazy function. Could be, well, the most simple example, one of the most simple examples is just that we have a function that kind of is defined for the points on the plane, right? We have some kind of surface, right? These points lie on the surface, and the surface is defined somehow. It hovers over the plane, and well, for each point in the plane, you have such a point in the space, and this is a function from R2. So to each point in the plane, we assign a real number. We can depict this function in R3, of course, and this has to be somehow smooth. Like this has to be without angles in order for the function that describes that to be differentiable, right? And somehow we don't know what it means exactly, but somehow I claim if it is differentiable, if it is somehow smooth, then there will be such a linear map L, and the function now I call epsilon from above, I just call it R, such that R x0 compared to above. Here, if we bring it to the side, and we have exactly that this difference between the function and its linear approximation, where linear L is of course now not a number, but L is a linear map itself, right? Linear map, just like in the definition above, I mean far above, right? L linear, such that this approximation again has the property that in the proximity of the point X, we have a very good approximation, which means that this difference goes to 0, and this difference is now displayed by this function r, right? And so that is x goes to 0. And here we use something which is called a norm, and a norm is just something like generalization of absolute value. We won't go into it for now, but if you know Euclidean norm, well, Euclidean norm you know, of course, but maybe you have never quoted that. Well, Euclidean norm is just what? Well, if you have an Euclidean norm, you have the Euclidean norm in R3 or Rn, you can imagine how it generalizes for Rn. You just have this point, and it has its three coordinates. I don't know, like coordinate y. So it has a coordinate y0. Oh, well, let's go to y tilde better. Has a coordinate z tilde, and it has a coordinate x tilde, right? P with coordinates x tilde, y tilde, z tilde. When the Euclidean norm of this point P, right? And when we talk about Euclidean norm, usually write such lower index 2 here, is just the length of the vector which connects this point with the origin. So maybe you also have seen that this vector could be also denoted as p, right? And this length is of course just by the theorem of Pythagoras. You can compute it yourself. This is really simple computation. This is just x squared plus y squared plus x tilde squared plus y tilde squared plus z tilde squared, square root of that, right? So So here it becomes the norm, because for general vector, of course, you can have an absolute value. What would that mean? But you have some generalization of absolute value that kind of has the same properties. And in this, it has to go to 0. Actually, that means exactly that the norm goes to 0, because the norm is actually the only reasonable way to measure the proximity of a vector to 0 in vector spaces. Right, so we are looking forward to some quite interesting things. We will be able to approximate a large class of functions, in particular such funny surfaces that are kind of smooth in their shape, kind of smooth, like they don't have angles. We will be able to approximate them by linear functions, at least approximately. Of course, it's an approximation, so of course it's approximate. Yeah, we'll be able to approximate them by linear functions, and that will give us many cool properties of such linearizable functions or differentiable functions, which is actually the same. Yeah, there's a lot to look forward to. And you can imagine that things like analysis or, well, calculus in one variable that generalizes to more general spaces, and we can do similar things like the fundamental theorem of calculus in one variable in higher dimensions, and we can have some awesome theorems. Oh, that is all to look forward to. For now, we leave it at this example, and you don't need to understand it rigorously, right? Because it was not rigorous at all. I have just shown you some thinking that one could do in mathematics, and which is really fun, as you probably have seen, I hope. So yeah, that's the examples for now. And for now, we stop here. Thank you very much for your attention, and we'll return next time to do some more.